Application of similarity criteria in geometric problems. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on the theoretical foundations of similarity, specifically the three core criteria: angle-angle, side-side-side, and side-angle-side. Now, here is the challenge you will face in your exams. In actual geometry problems, these criteria are rarely handed to you on a silver platter. You won't simply see a note saying, "These triangles are similar by SSS." Instead, the real work lies in the investigation. You will need to use other geometric properties, things like the properties of parallel lines to find equal angles, or even algebraic manipulations to find proportional sides, to actually prove that these criteria are met. In this tutorial, I am going to show you exactly how to bridge that gap. We will learn how to apply these similarity rules to solve much more complex geometric problems by breaking them down into clear, logical, and manageable steps. Let's get started. Using parallel lines to prove similarity, AAA criterion. Whenever you are reading a geometry problem and you see the words parallel lines, I want you to take note immediately. This is a massive hint from the examiner that you should be hunting for equal angles. You see, when parallel lines are intersected by a transversal line, they create specific patterns, specifically equal alternate interior angles and equal corresponding angles. To solve these types of problems systematically, I want you to follow this logical flow. First, identify your parallel lines, locate them clearly in the given figure. Second, find your equal angles. Use those properties of alternate interior or corresponding angles to find at least two pairs of equal angles. Third, apply the AA criterion. Once you have proven those two pairs of angles are equal, you can officially state that the triangles are similar by the angle-angle similarity criterion. And finally, establish proportionality. Now that similarity is proven, you can write out the ratios of the corresponding sides to solve for unknowns. Let's look at a real-world example to make this concrete. Imagine a street light standing vertically with a person standing nearby. Because both the lamp post and the person are perpendicular to the ground, they are both vertical, which means they are parallel to each other. As the sun shines, it creates shadows, forming two triangles. Let's apply our steps here. Step 1, we've identified that the lamp post and the person are parallel. Step 2, the sun's rays hit both the person and the post at the same angle, creating an equal angle at the tip of both shadows. Step 3, since both triangles have a 90-degree angle from the vertical position and they share that same angle from the sun, the triangles are similar by the AA criterion. Finally, step 4, because we have established similarity, we can set up a proportion. We can say the height of the post divided by the height of the person is equal to the length of the post's shadow divided by the length of the person's shadow. This allows us to calculate the height of the post using the shadow lengths. Now that we've established that similarity criteria like AA, SSS, and SAS aren't always handed to us on a silver platter, let's look at our first practical strategy: using parallel lines to prove similarity. In the next slide, we will move away from parallel lines and look at how we can use side lengths alone to find unknown angles using the SSS criterion. Finding unknown angles using SSS similarity. Now that we've seen how parallel lines help us find equal angles for the AA criterion, let's shift our focus to a different approach. On this slide, we are looking at the SSS, or side-side-side, criterion. What makes SSS so unique is that, unlike the previous method, it allows us to prove two triangles are similar using only the lengths of their sides, without needing to know any angles beforehand. However, the moment we establish that these triangles are similar, we gain a powerful tool. We can conclude that all their corresponding angles are also equal. To solve these problems systematically, I want you to follow this logical flow. First, list the sides. Identify the lengths of all three sides for both triangles. Second, calculate your ratios. A pro tip here: always pair the shortest side of the first triangle with the shortest side of the second, the medium with the medium, and the longest with the longest. Third, verify proportionality. You are checking to see if the ratio of side 1 over side 1 prime equals the ratio of side 2 over side 2 prime, which also equals the ratio of side 3 over side 3 prime. Fourth, if all these ratios are identical, you can officially conclude the triangles are similar by the SSS criterion. Finally, once similarity is proven, you can equate the angles. Identify which angles sit between the corresponding sides and set them equal to find any unknown values. Let's look at a concrete example to see this in action. Suppose we have triangle ABC with side AB equals 3 centimeters, side BC equals 4 centimeters, and side AC equals 5 centimeters. We also have triangle DEF with side DE equals 6 centimeters, side EF equals 8 centimeters, and side DF equals 10 centimeters. Following our steps, let's compare the ratios. First, AB over DE is 3 over 6, which simplifies to 1/2. Next, BC over EF is 4 over 8, which also simplifies to 1/2. And finally, AC over DF is 5 over 10, which is also 1/2. Since all three ratios are equal to 1/2, we can state that triangle ABC is similar to triangle DEF by SSS similarity. Because they are similar, we know the angles correspond perfectly. Angle A equals angle D, angle B equals angle E, and angle C equals angle F. So, if the problem tells us that angle D is 60 degrees, we can immediately conclude that angle A must also be 60 degrees. This brings us to our next topic, where we will see how to handle even more complex problems involving the product of sides and the SAS criterion. Product of sides and SAS similarity. Now let's move on to slide 4, where we tackle a slightly more advanced technique. Up until now, we've looked at cases where the ratios or angles were given directly, as we saw in our discussions on parallel lines and SSS. However, in more complex problems, you won't always see a nice, clean ratio. Instead, you might be presented with a product of lengths, something like OA times OB equals OC times OD. To use the SAS, or side angle side, criterion here, your first goal is to transform that product into a proportional ratio. Let's walk through the logical flow to handle this. First, you must rearrange the equation. You want to move the terms around to create a fraction. For instance, if you start with OA times OB equals OC times OD, you can divide both sides to show that OA over OC equals OD over OB. Second, once you have your ratios, you need to identify the included angle. This is the angle trapped specifically between the two sides you just worked with. In many geometry problems, a great place to look is for vertically opposite angles, which we know are always equal. Third, once you have confirmed that two sides are proportional and the included angle is equal, you can officially apply the SAS criterion to declare the triangles similar. Finally, once similarity is established, you can derive further results, such as finding any remaining missing lengths or angles. Let's look at a concrete example to tie this all together. Imagine we have two lines, a B and CD, that intersect at point O, and we are given the information that OA times OB equals OC times OD. In step 1, we rewrite that equation as a ratio. OA over OC equals OD over OB. In step 2, we look at the intersection and observe that angle AOD is equal to angle COB, because they are vertically opposite angles. In step 3, we check our criteria. We have two sides in proportion, and the included angle AOD, is equal to angle COB. Therefore, in step 4, we can conclude that triangle AOD is similar to triangle COB by the SAS similarity criterion. This technique is a vital bridge to the summary we are about to see in the next slide. Key takeaways. First, remember that whenever you see parallel lines in a geometric figure, your brain should immediately think of AA similarity. Your goal here is to hunt for equal angles, specifically looking for alternate interior angles or corresponding angles created by a transversal. Second, if the problem provides you with the lengths of the sides, you are looking toward SSS similarity. The key rule here is that if you can prove that all three pairs of corresponding sides are proportional, you can then confidently conclude that the corresponding angles are equal. Finally, if you encounter a problem involving the product of sides, for example, where x times y equals z times w, you should aim for SAS similarity. Your first step is to algebraically convert that product into a ratio, such as x over z equals w over y. Once you have that ratio, look for an included angle, such as a shared angle or a pair of vertically opposite angles, to complete the SAS criterion. Now that we have walked through the specific strategies for AA, SSS, and SAS similarity, let's pause and summarize the key takeaways from today's lesson so you can use them as a quick reference guide. Keep these three logical connections in mind, as they are the foundation for solving almost any similarity problem. In our next slide, we will discuss some common pitfalls to watch out for so you don't lose marks on these tricky details. Common mistakes to avoid. First, watch out for incorrect vertex correspondence. This is, hands down, the most common mistake I see. When we say, triangle ABC is similar to triangle DEF, we are making a specific claim about which angles match. This means that the ratio of side AB to side D must equal the ratio of side BC to side EF. If you accidentally write the ratio of AB over EF, your entire calculation will be mathematically incorrect. Always, and I mean always, double-check that your vertices match up in the correct order. Second, do not confuse similarity with congruency. It is easy to slip into thinking that because the shapes are the same, the sides are the same length. Remember, similarity means the shapes have the same proportion, but they are not necessarily the same size. You cannot assume that side AB is equal to side DA. You can only assume they are proportional. Third, be careful not to ignore the included angle when using the SAS criterion. As we discussed in the previous slide regarding products of sides, the SAS rule is very strict. The angle you are using must be the one trapped directly between the two proportional sides. If that angle is located elsewhere in the triangle, you simply cannot apply the SAS similarity criterion. Finally, avoid an incorrect ratio setup when working with the SSS method. When you are checking if three sides are proportional, do not pick sides at random. To stay organized and accurate, always compare them in the same order: smallest side to smallest side, medium to medium, and largest to largest. If you mix up the order, you will likely reach the wrong conclusion about whether the triangles are similar. Now that we have covered the various methods for applying similarity criteria, I want to wrap up this tutorial by discussing some common pitfalls. Even students who understand the theory often lose marks due to these specific errors, so please pay close attention. If you can avoid these 4 mistakes, you will be well on your way to mastering geometric similarity.